In this video, we're going to take a look at the chemical equilibrium and acid-base questions from this paper. Consider the balanced equation for a hypothetical reaction that takes place in a 2 cubed sealed container. So we've been given the reaction, and they tell us that graph A is obtained at 298 Kelvin and B at 398 Kelvin. In other words, the temperature is not really important, just that that's a low temp and this is a high temperature. So question 6.2, what do the parallel lines after T5 in graph A tell us? Well, it tells us that equilibrium was reached, right? Question 6.3, is the forward reaction exothermic or endothermic? So I'm going to refer to graph B when I'm answering this, because in graph B, we increased the temperature. But also, we noticed that the amount of product decreased. The amount of product decreased. So that tells us that the reverse reaction was favored, right? Because of that. Now, an increase in temperature favors the endothermic reaction. So if the reverse reaction was favored, it means that the reverse reaction is endothermic. That means the forward reaction is going to be exothermic. Explain the answer to question 6.3 we've already done so. Question 6.5, how does the value of the Kc for the reaction in graph B compare to graph A? So there was a temperature change, so definitely Kc is going to change. So what's going to happen? So this is 6.5. Since the amount of products decreased, the Kc is going to decrease. Question 6.6, the equilibrium constant Kc is 0.49 at 398 Kelvin. Calculate the initial number of moles of P2Q. So here I will do a rise table. So P2Q, I'm not going to include the Q because it's a solid. So I'm going to have a solid double line here, and then 2PQ2. Now RICE, the ratio is 1 to 2. Initially we don't know, change we don't know, but at equilibrium, do we know anything? Yes, we do. At equilibrium we know the concentration of the P2Q, it is 0.35, and we know the Kc. So Kc is equal to, it's going to be the concentration of PQ2 to the power of 2 divided by the concentration of P2Q. Now, since the Kc is 0.49, that's going to equal 0.35 squared divided by the concentration of P2Q. The concentration of P2Q then at equilibrium is going to equal 0.35 squared over 0.49, which is 0.25. So this is going to be 0.25. Now, they tell us that it was a sealed container. So that simply means that here initially we are going to have 0. Then the change is going to be plus 0.35. Now the change column is the change row rather is one of the most important rows in this rise table, or in any rise table, because we're going to use the ratio to figure out the change. So if this change was plus 0.35, this is going to be minus, since it is a reactant, and it's going to decrease in the ratio 1 to 2. So this is actually going to decrease by half of 0.35, which is 0.175. So to figure out what the initial amount was, we're going to say 0.25 plus 0.175, which is 0.425. This is the initial concentration. If you want the number of moles, you can take the concentration and multiply by the volume, which we know. So the number of moles is going to equal C times V, 0.425 times 2, which is equal to 0.85 moles initially. Okay. Question 6.7, describe the change made in the equilibrium system at T8 as shown in graph B at constant temperature. So what's going on here is I can see that for both the graphs, there was a decrease in the concentration. So it's not going to be that something was removed. Rather, the way that you can decrease concentration is by increasing volume. So if you increase the volume, then the ratio of the number of moles to the volume, the concentration, is going to change. If I increase the volume, the concentration is going to get smaller because the number of moles is the same. And explain using Le Chatelier's principle how the system reacts to the change. So if I increase the volume, there is an effect. Increasing the volume decreases the pressure. So if the pressure decreases, the system will want to favor the side that has more molecules. If you look at this reaction, this has one molecule and this has two molecules. We ignore the solid. So the system is going to favor the forward reaction. So PQ2 is going to increase, whereas P2Q is going to decrease. And that is what we are observing in this graph. You can see that P2Q is increasing and the other decreases. Now let's take a look at the acid-base question. A standard solution is prepared by dissolving 10 grams of sodium carbonate, Na2CO3, in 0.7 dm cubed of water. Calculate the concentration of the solution. So concentration is equal to mass divided by molar mass times volume. The mass is 10, the molar mass is 106, the volume is 0.7. That gives us a concentration of 0.13. Moving on to the next question. Will the pH be greater than or less than 7? The pH is going to be greater than 7. 7.1.3, write an equation that explains the answer. So Na2CO3 is going to react with the water, right? It's dissolved in water. And so when that happens, we are going to get H2CO3 and NaOH. The NaOH, the OH rather, is going to make the solution basic. There is another reaction that you could write. You could say Na2CO3 plus H2O is going to give you NaHCO3 plus NaOH. Now, of course, you do need to balance it, but the idea here is that the formation of NaOH, or OH rather, is going to make the solution basic. Moving on, the sodium carbonate solution is titrated with dilute hydrochloric acid. The following indicators are available. Which of the following indicators is most suitable? It's going to be indicator P. Give a reason by referring to the data in the table. So we would use indicator P because sodium carbonate is a weak base. And when you react a weak base with a strong acid like hydrochloric acid, you are going to get an acidic salt. So you need to use an indicator that is sensitive to those lower pH values. Moving on, when 0.01 moles of dilute sulfuric acid, H2SO4, is mixed with 0.024 moles of potassium hydroxide, the total volume of the final solution is 0.2 dm cubed. Let me just sketch this out. So here I have 0.2 dm cubed, and in here I have H2SO4, I have 0.01 moles. I also have 0.024 moles of KOH. What is meant by, okay, leave that out, 7.2.2, calculate the pH of the final solution. So what we'll do here is we'll first start by trying to figure out whether the pH is going to be greater than 7 or less than 7. And to do that, I need to figure out whether I'm going to have acid in excess or base in excess. So I'm going to do a quick ratio. I'm going to do a ratio between KOH and H2SO4. Now from the reaction they've given us, the ratio is 2 to 1. 2 to 1. Now I'm going to assume that I don't know the KOH. So let's call that X. And the amount of H2SO4 that I have is 0.01. If I cross multiply, X is going to equal 0.02 moles of the H2SO4 that's needed. However, we have 0.024 moles. Oh, sorry, this is the KOH, right? But we have 0.024 moles of KOH. That means we have more than we need. So simply put, the KOH is going to be in excess. So KOH is in excess, right? So the amount that's in excess is going to equal 0.024 minus 0.02, which is 0.004 moles. Now this 0.004 moles is sitting in that 0.2 dm cubed solution. So I can calculate the concentration. So the concentration of the KOH is going to equal number of moles divided by volume. The number of moles is 0.004, volume is 0.2, and that gives us 0.02 moles per dm cubed. Now, because KOH is monoprotic, the concentration of the KOH is going to be the same as the concentration of the OH minus. So we can say, therefore, the concentration of the OH minus is equal to 0.02 moles per dm cubed. Now, I can calculate POH from here. POH is equal to minus log the concentration of OH minus. So that's going to be minus log of 0.02. That gives me 1.69897. So pH plus POH is equal to 14. That means pH is equal to 14 minus 1.69897, which is equal to 12.30. And that's it. Thanks so much for watching. Good luck for tomorrow. Bye.